Welcome to the third and final installment of the Link ECU training series. Today we're going to be focusing on drivability and ignition timing. So I kind of held off on this video because ignition timing can be the dangerous part for tuning, and a lot of tuners will get a bad rap for blowing up someone's car because of timing and pre-detonation. If you haven't heard of it, we'll go into a little bit of background before we actually get started building our maps. But it can be extremely dangerous, and that is almost the number one cause besides going lean and boost as far as blowing up motors. So I do want to take some precautionary steps and educate you guys before we really get into a lot of the changes, because this can be dangerous. So if you don't know about pre-detonation or knock, I would highly advise not skipping over this first section. Some of you may have seen this chart from a couple other training videos, but let me just explain. Your ignition timing is the time in which your spark plug fires in relation to crank angle. Here in the middle, you have a line that's top dead center, and you have ignition before and after top dead center. Normal combustion would happen slightly after top dead center, and as your RPMs go up, your ignition timing goes up as well, usually up to a certain point, and we'll cover that shortly. Any kind of ignition before top dead center will produce combustion outside of the actual combustion chamber, aka backfires or flames or whatnot. So a lot of people will put in decel tables negative numbers, and that will produce the combustion event not happening inside your cylinders of your motor and in the exhaust, and yeah, that's how you get the flames. So here, if you advance the timing too much, your cylinder pressure will spike, sometimes 2 to 3 times what a normal combustion event cylinder pressure in PSI would be. For example, this one is at 800 for the cylinder pressure when the spark event actually happens. And if there is a detonation or pre-detonation event going on, that cylinder pressure is going to spike massively and suddenly. And usually what happens is you'll crack a piston, the top of the piston will just crack, or you'll break a ringland on the side of the piston because your combustion pressure is trying to leak down past the rings, and your rings can only do so much on the sides of the piston, or you'll bend a rod. So at that kind of PSI, especially if you're already running like a crazy amount of boost and you hit pre-detonation and you're at like 20, 30 PSI boost, you don't have much wiggle room as far as cylinder pressure goes. That'll put you way over the safety limit for your pistons and combustion chamber, and something's bound to break. So there are ways we can detect detonation. Usually it's a pinging sound. Sometimes if it's bad enough, you'll hear it audibly, and at that point you're already doing damage to your motor if you can physically hear detonation. But most of the time your car is going to have knock sensors, either a narrowband or wideband knock sensor, and that'll pick up very, very subtle spikes in sounds that's going to produce as far as pre-detonation or knock goes. So your knock sensors are extremely important, and that's the first thing I'm probably going to want to cover in this training series, setting up your knock sensors properly, because it is so detrimental. The other thing you can do, if your car doesn't have knock sensors, they sell a knock block device, link cells, and you get like a pair of headphones, and it's hooked up to a knock sensor in this little transmission box, and you can audibly hear the knock through a set of headphones. I believe you can also hook it up through the CAN bus system and integrate it into the Link ECU, and it will actually pull timing if it detects knock to save your motor. So, and sometimes the factory knock sensors aren't that great, because I know, like for example on the S2000, it's a narrowband sensor, and it only detects at a very, very specific frequency and range. So a lot of times the knock window and frequency will change depending on RPM. So factory knock sensors are tuned to a certain window where knock could happen. So for a narrowband knock sensor, you're only looking at a very small window, usually in the higher RPMs, and then not getting any data in the lower RPMs. So usually you'll get a wideband sensor like a Bosch style donut knock sensor to throw on the block, usually in between groupings of cylinders. So let's say you have a 6-cylinder, it would be kind of in the middle. And then as far as like V8s, it would usually be in like the valley of the motor itself, kind of like LS motors. But yeah, so there's a lot of different style knock sensors and stuff, but what you have to do is set up in Link software the specific frequency and knock threshold to detect if it's actually knock or just noise from the motor. Because sometimes certain motors are noisy as far as valve train goes, and sometimes you'll get piston slap that can be kind of mistaken for knock. So a lot of different variables, so we're going to run through that. One last thing I did want to cover is, again, if you don't have any knock sensors, what you could do on a dyno is hold the car at a specific load cell, and you would actually live increase or decrease the ignition angle, and you'll see a torque increase or decrease. Now you'll get to a point where you'll have sort of a peak cylinder pressure, and that's going to create the most amount of power. And then any crank angle above or below that, you're going to yield less power. So you really want to get a dyno and kind of roll into a specific cell or area and kind of jump around in the different parts of the map to dial in peak torque. So that's how you get the absolute most of an engine. And then usually you'd probably dial it back like 1 or 2 degrees after that. Everyone that shows, doing a dyno pull, just one solid full pull, they're not doing any sort of like ignition timing changes. That's usually a fueling thing to get fueling dialed in across the board. But to get the absolute most out of the motor, you do want to hold the car at certain load cells, and you can't do that on the street, obviously. All right, so again, the most important part is going to be setting up your knock sensors. And a lot of these base maps, so I'm looking at the one for my S2000, and a lot of this is pretty dialed in, but if you're setting this up from scratch, usually, so if you go into knock control, knock setup, there's the knock mode. So if you do detect knock based on your parameters, this is the after effect of what's going to happen and what the ECU is going to do. So mine I have set as ignition trims, so mine will dial back ignition timing. You can also do just fuel trims, or you could do ignition and fuel trims, so add more fuel to cool down that cylinder a little bit to help with the knock. And there's a couple other different modes, but usually, especially factory ECUs, they'll just pull a little bit of timing. And there's a ignition trim setting panel here we're going to go over after, which shows the frequency or how fast it's going to pull timing or how much timing to pull and how aggressive it does it. So here's what I was talking about as far as your narrow band versus wide band. There's all kinds of different narrow bands in here, and I believe, there's 2 different wide bands. So I think one of these is the Bosch donut style common knock sensor that everyone uses. And then you would just have to look up what factory narrow band you have for your particular car. This gain channel talks about an amplifier. So remember I was saying some motors can be noisier than others. So this is like turning up the volume in which the ECU listens for knock. So if you have a super noisy motor, you'd want to turn the gain down. If you have a pretty quiet motor and the knock is very distinguishable from normal engine noise, you can turn the gain up a little bit. You can also change or clear out the trim table. So it will build over time a table in which it detected knock and ended up pulling timing based on that. So here is a very good thing to look at if you want to, when you power cycle the ECU, clear that table or hang on to it. I would particularly like turning this off because I want to get a history of if I had knock or not in my trim tables. And it's per cylinder too, which is also really good. So if you have a particular cylinder that's having issues, like maybe start looking into that one cylinder is leaner than others, or that one cylinder maybe has a leaky valve or something else going on. You'll kind of get an indication of the health of the motor. And then these are your lockout conditions and TPS conditions. So there's a lot of parameters on how you can set it up. The second screen here is if there's a delay. I don't know why you'd want to delay that. If you have an ignition spark event, you can change all that here and how aggressive you want to get with pulling timing. So some ECUs get really crazy with it and pull like 3 to 5 degrees as soon as there's a knock event, because the closer you are to that knock limit, again, that cylinder pressure you go spike up like crazy. So usually the 1 degree per percent is fine. And then we have some allocation tables. You don't have to really mess with these too much. It depends on how many cylinders you have, obviously, and your firing order. So make sure that's all set up. And there is some documentation. I'm going to cover that in this video because it would take hours if I were to go over every setting. But your knock threshold is here. So this is talking about the frequency and volume in which, based on RPM and TPS, it's looking for knock. So sometimes at lower RPMs, you would want to have a lower sensitivity, and at higher RPM, you would want to have higher sensitivity for knock. And you can actually log the knock threshold values as you're driving to kind of mess with these values a little bit. Usually that's how that's set up. And then I was talking about the ECU storing the knock data and how much it trimmed back that knock event. And here you would have degrees of timing in which the ECU had to pull timing to get that knock to go away. So if you have a whole section here that has like, I don't know, -2, 3 degrees, 4 degrees, whatever, you have to start pulling ignition timing in your main ignition timing table. So that's what that is. So again, before you start with your actual ignition timing table, make sure all of this is set up and good to go. Sometimes what I'll do is, to get the thresholds right, I'll actually purposely get the car to knock a little bit at a certain RPM. So I'll hold it at 4,000 RPMs or whatever and start increasing the ignition timing. And then you'll see that knock value go up in the log. And then you can kind of see, okay, this is normal engine noise versus what knock would be. So you can kind of play with that a little bit. At low RPM, when you get knock, and especially when the car isn't moving under a load, it's not too bad. But that's usually how I set this up, is I'll just stationary hold the RPM and mess with the ignition timing until introduce the knock. All right, so we're gonna work on tuning our main ignition table, and you're gonna usually say, well, how the heck do I even start this? And there's really a couple different ways to do it. You can base this on your stock ECU's timing, and you can look in forums for your particular vehicle. I know a lot of Hondas, they'll have the Honda data base tables, which has the factory ignition timing. So you can look at other ECUs tuning platforms and see what the base ignition is set at for that. You can look in forums for your car, but the information is probably out there for your factory ignition timing for your motor. If it's a super unique custom build and you're just completely starting from scratch, I do have one trick I want to show you. So this is a little known gem I found a while back and bookmarked it, and I'll try to provide the link in the description of this video, but Megasquirt a long time ago had posted a utility to create an initial spark table. So you would enter your cylinder bore, you can also do in cc's, what kind of, if it's a 4-valve motor, what kind of fuel you're using, what the compression ratio is of your motor, and what kind of vacuum you see at idle, and that will set the lowest numbers, I think, on your table. The highest boost value you would see, and then your max RPM, what your idle RPM would be, all that kind of information, and you can change the table size. And once you enter all this information, it will actually generate this file. Now, you can sort of probably interpret what this is saying. So the x-axis is going to be these guys, y-axis is these guys, and then here's your actual ignition table here. So this will get you in the ballpark if you have absolutely no information on your motor, or it's super custom, like you have crazy cams or ITBs or something. I actually use this on an E30 with ITBs to get a base table started, and it ended up working out pretty well. But you can also load this into the Megasquirt software, and it will display it in a table all nicely, and then you can copy it over to the link table. So that's one way to get you started, at least. In order to keep the motor safe, you have to start pulling timing once you get into boost. Usually what I do, if I have a pretty good base table of a factory engine and I get all the values in the table, and then my y-axis is going to be the map sensor pressure. So here would be somewhere in vacuum down here. And then anything above 100 kPa is going to be boost. And I had cleared this out for a specific reason, and I'll show you here in a second. So here would be like a couple pounds of boost. I forgot the exact equation to convert kPa to psi of boost, but again, anything above 100 is above atmospheric pressure, and you're building positive pressure in your manifold. So the general rule of thumb to start off with is for every kPa above 100 kPa, so this would be 20 above 100, you're going to pull 0.3 degrees of timing. Let's take this example here at 4,500 RPM. So we're at 30 degrees at 100 kPa, and we want to 20 times 0.3. So that's taking away 6 degrees. So you do 30.2 minus 6. So you want the cell to be at 24.2. Okay. And you would do the same thing for 140. You do 40 times 0.3, and that's how much timing you need to pull. And then that would be, again, from this 30.2 value into this cell. Now, when you start getting down to where you're reducing so much timing where it's pretty much at TDC, that's pretty much going to be the limit for your motor and how much boost you can run. So that's how you can kind of figure that out. And once you start getting into negative timing, you're gonna just start adding a crazy amount of heat to your exhaust and manifold, burn out turbos and things like that, and it won't even produce any power. And the benefit to having higher octane fuels is, let's say you're running 100 octane or E85, and at 100 kPa, you can run, I don't know, let's say 40 or 50 degrees of timing here. You have more headroom for reduction once you get into higher amounts of boost, if that makes sense, right? So you just can run more timing across the board, run more boost, the motor's happier, and whatnot. So that's kind of how that works. And again, I would set this using that 0.3 degrees for every kPa of boost rule to start with, and then go for a drive and do some logging of the knock sensors, or on your dyno, just see if you're at peak torque for that RPM range. If not, you can go higher or lower for timing. So that's how all that stuff works. If you guys have any questions, let me know in the comments, because I know that can be a little bit confusing to set up, but once you get the hang of the math, you can start populating the rest of the higher boost cells. One thing I did want to mention before we get into some of the drivability settings, and this kind of goes into drivability, I guess, but the idle area here is actually very important to get a steady idle. I know a lot of people rely on their idle control valves and stuff like that, but if you don't have timing correct at idle, and you're just going to be hunting issues and try to play with fueling and all kinds of stuff to chase your tail with to getting a steady idle, and that's especially the case when you start getting into really aggressive camshafts and ITBs. ITBs can be very tricky to get to idle correctly. So the trick that I do to get idle correct, and a lot of tuners will keep this a secret, is I will log manifold pressure, and if you play with timing, you'll see that your manifold pressure will go up or down. And what you want to do is, as that number is moving around and you're changing this ignition timing, you want to get your vacuum as absolutely high as you possibly can with your ignition timing settings. So a higher vacuum here would actually mean a lower kPa value. So 0 would be like extreme vacuum. Most motors can't get to 0, but in my table probably isn't set up all that great. My car likes to idle probably between the 20 and 40, probably like 25-ish. So you actually want to, in your y-axis, make this a little bit more granular so you get that exact range of the vacuum in which your car is idling to really dial in the ignition timing and higher resolution. So the steps on this y-axis and x-axis, I like to have the idle area high resolution. So spread these numbers out that jump from 0 to 60. I would probably span these out even further. And then kind of like the middle area doesn't matter as much. And then like high boost area doesn't really matter that much either. But again, you can come in here to axis setup, and mine, I'm not even using all of the available slots for the y-axis. So I can go higher boost or use more of the cells for the lower manifold pressure. So it's up to you guys, but again, higher resolution at idle to get that really dialed in is going to be key for drivability. Okay, so after you have your idle base table set up in that idle area and you have your fueling correct, then you can pretty much move on to the idle speed control factors. So if you have a idle control valve which opens and closes and lets extra air into the motor or chokes it off to get that idle steady to your target idle speed. That's how that works. Some cars don't actually have ICVs, so it's all going to be ignition timing based. So that's even more important to get your ignition timing in the previous step as close as possible. But there are variables as you're driving. Your car could stall out as you're coming to a stop, which is really common. It doesn't catch idle. A lot of people will complain about, and that all comes down to your idle speed control. So I'm actually starting at the idle target speed table. So the top is actually going to be engine coolant temp, and then what you want your RPM target to be at that specific engine coolant temperature. So when the motor's warming up and is cold, obviously you want that a little bit higher, and then to taper off when the motor's fully warmed up. So mine's actually set at 950, and there is also the AC offset table. So usually when you turn your AC on from the factory, that compressor clutch kicks on and it creates a lot more load on the motor. And usually you have to spin the motor a little bit faster to compensate for that AC compressor to be on. So these are kind of arbitrary numbers. And this bumps up the idle a little bit in terms of your base idle for the AC. You would actually need to have also your AC switch hooked up to the Link ECU as an input to tell that the Link ECU that your AC compressor clutch actually engaged. So that's kind of its own system. So here's your basic setup for idle speed control. Again, if you don't have an idle control valve, you could turn this off. You can also leave this on if you want to just do ignition control only. So there's all different kinds of idle control valves you can use. And this is kind of interesting too. So there is the mode is open or closed loop. And what that means is open loop, it will base itself on a specific idle base position table. So I think I have that. Yeah, so this is mapped out specific characteristics of my idle control valve, which are apparently known values. This was just set up in my base table. If you don't have that, I would personally just set that to closed loop, and that will automatically correct the difference between your target engine speed and your current engine speed. The Link ECU will automatically change the ICV value for that. Sorry about that. I'm on a virtual machine here, and sometimes the software is unstable in that environment, but there are some more in-depth idle controls, and you can read all about those in the help section, but you can get really granular with idle speed, and this is probably one of the most advanced idle control pieces of software I've seen in a while. So if there is a specific scenario, and sometimes if you have an automatic transmission and you go from park to drive, sometimes that can cause the car to stall. You can account for that, and there's all kinds of conditions built into the Link ECU that will compensate for all kinds of different scenarios. One thing I like to look at too is the lockout. This is where the idle speed control will turn off after a certain RPM above the target. And that's pretty important because you can actually get rev hang issues. Same with this TPS percent lockout. So if you suddenly let off the gas and your idle speed control doesn't kick in, the car is going to stall. So you want to make sure that these values are going to be at a throttle position percent in which you're actually letting off the throttle and this idle speed control is picking back up. So you have to play around, because I've had this issue on my personal car where sometimes I would let off the gas and my TPS value would be at like 1% instead of this 0.8 value. and my car would stall because idle speed control isn't kicking on because it's been locked out based on these parameters. So, and again, the map value, so manifold pressure, if you're below a certain manifold pressure, you can tell this to lock out the idle speed control. So these three settings are going to be crucial for having your car catch idle, quote unquote, when you're coming to a stop or letting off throttle. Kind of jumping around here back to the ignition timing stuff. And one thing you want to look at too is the under ignition, the engine coolant ignition trim and IET ignition trim. So if your intake temps start to get higher, you have a greater chance of getting knock or pre-detonation. So here you can actually go into a 3D table, and here I have set up, so this is in Celsius, so above 50 degrees Celsius for intake air temp, I start pulling timing and then get super aggressive pulling timing if the intake air temps are super high. Same with the coolant temps, because if your coolant temps are high, all that coolant is surrounding your cylinder walls in the coolant jackets surrounding that. So as your coolant temps get higher too, you also want to start pulling a little bit timing. So here's that up here. So at like 110, I'm starting to pull it, and then up to 140. So that's a good engine protection thing to turn on. And a lot of factory ECUs have this stuff built in, and you probably don't even realize it. That's why, like, as you know, in the summertime, if it's like 90 to 100 degrees outside and you're trying to rip on your car, it feels slower. Well, that's why, because your stock ECU is pulling timing. All right, so one other thing that has to do with idle, and I kind of touched on this a little bit in the last video, I think, but the overrun fuel cut settings and the overrun deactivation table. So if you're still finding that you've adjusted your idle settings correctly, and when you're coming to a stop that it's still dying when you let off the throttle coming to a stop, usually it's these overrun deactivation table settings. So it actually says in the instructions here that you want to be typically a little bit higher with this value than your target idle. Yeah, so it says 500 RPMs. So this value has to be 500 RPMs higher than your target idle speed. So let's say your target idle speed is, 1,000 RPM. You would want this overrun fuel cut set to 1500. Then the other thing here is your overrun fuel cut settings. So personally, when I'm racing my car and not really street driving and dealing with gas mileage or care about gas mileage as much, I'll put pretty lazy settings on the overrun fuel cut. And what that does is when you let off the throttle, these settings will kick in and tell it to just completely cut off fuel from dumping on deceleration. And that has kind of two implications. You have quite a bit more engine braking if you have overrun fuel cut turned on, and that can make your transient throttle, so that on and off throttle. So like, let's say you're setting this up for a drift car. If you're just whacking the throttle back and forth and it's hitting that fuel cut, that overrun fuel cut, that's going to be super annoying transition wise. So in that case, if you're really aggressive with the throttle, you can make this a little bit lazier too. And a way to do that is the activation delay. So I have mine set at 2 seconds. So 2 seconds after you let off the throttle, then the fuel cut will turn off on. So if I'm in a racing application and I'm cornering or something and I'm just like lightly tapping the throttle on and off completely, I don't want this fuel cut setting to come into play. But if I'm on the street, for example, and I am like decelerating down a super long hill or something, I will then have these overrun fuel cut settings turn on. So it can also pull ignition timing, and there is a torque reintroduction time. So again, this is how fast it's going to react when you get back on the throttle. So if you had a weird transient throttle problem where it would kind of stutter between on and off throttle, I would also look into this torque reduction time. I reduced mine quite a bit on my car, I remember. And then again, your TPS threshold is going to be very important, because if you let off throttle and your TPS percent completely closed throttles at like 1% and this never kicks on, then yeah, it's not going to work. So a lot of these settings, especially the motorsport stuff, like the anti-lag and all that, are going to have the TPS thresholds too. So always log your TPS values, fully open, fully closed. Make sure you calibrate your TPS, which you should be the first step you do, covered in my other video, and make sure you're absolutely meeting the criteria for all these different modules within the ECU, because they're looking for specific conditions in which to activate. Another drivability thing that I didn't cover in the last video is going to be your warm-up enrichment table. So that's going to be under fueling, and then your cold start, and then warm-up enrichment. So you can also have pre-crank prime, crank enrichment, whatever. So if you're having trouble cranking the motor and getting it to turn over, you can modify that table. But the warm-up is something that a lot of people don't really pay attention to, because up to a certain point or a certain time, your wideband O2 sensor is going to kick on anyways, and it'll start going into closed loop mode and try to correct fueling. But here you can actually get your warm-up enrichment closer by monitoring your lambda correction values, and then adding a bunch of fueling if it's super cold out to help out that closed loop mechanism a little bit and get it closer. These ECUs do have launch control, and usually I'll put this in single launch control or single launch RPM. I know a lot of guys will mess with this for drag racing quite a bit. I played around with it a little bit. One thing that's cool is you can set activation control as any input on the ECU. So let's say you have like a button or something on your steering wheel, you can activate it through there. I actually had mine set to always on, and I would have it set to a certain TPS and speed. So if I was at like below, I don't know, like 5 kph or miles per hour, and I had like over 90% throttle, my launch control would turn on and pretty much do whatever you want it to do. So in my scenario, I had it pull a bunch of timing to essentially you would go negative timing to be able to spool a turbo up. So remember I was saying that when you start pulling timing before top dead center into the negative values, you're actually going to start heating up and having your combustion happen inside your exhaust manifold instead of inside the motor. So that's why a lot of guys will get super aggressive with negative timing to help spool up a turbo. So you can do stuff like that. And then there's all kinds of hard cuts and things like that. But I'm not going to get into the details because I'm not really a drag racer. But just figured I'd cover that. There's also anti-lag, which is very dangerous for vehicles, but those are available to you as well. Wow, there's a lot of settings in there. I haven't really looked into this too much, but personally, unless it's like a rally car, you have a specific reason to do this, I wouldn't use it. If you want deceleration flames, you could always set the overrun fuel cut to off, and then in your main fuel table in the deceleration area, you can add a bunch of volumetric efficiency, and that will dump fuel. And then in your main ignition table, you can also set so like higher RPM in vacuum. You can set these to like 0 or like -10. I think it'll let you do that. Yeah. So Here you can use that to shoot flames as well. Again, that'll burn up your exhaust valves. It's not great for turbos, so just keep that in mind. I don't personally advise it or turn it on my cars, but it's how you do it. And videos that I have how to do that get a lot of views. So figured I'd cover it at least. But that's pretty much it for drivability. I know there's a lot of other little settings I've changed in the past. I'll have to go back through and check. But drivability wise, my car is pretty good. With the standalone, it feels like a factory vehicle and there's not really much I had to change. But again, if you guys have any questions, let me know. But I'm glad we covered the ignition timing stuff because a lot of you guys had questions on that and want to know when it was coming out, and the drivability and idle and decel settings, because that can absolutely make or break the way your car drives. So again, if you have any specific weird scenarios that come up, let me know and I'll try to answer them. But I think that's gonna do it for today's video and the end of the series. So thanks for watching.